go, we can begin.
Okay, good. Excuse me, just one question. Am I Okay. Good afternoon, everybody. My name is Simone Pirrotta, and I work at the Italian Space Agency. I work in a department that is named Exploration and Observation of the Universe. So we take care of missions that are related to space science in general, so astrophysics, but also exploration mission for the solar system. But today I will describe LICIAcube mission. I'm in charge of this mission as project manager, and as you probably know, LICIAcube will be the DART small travel companion for the mission that will start in 2 days. So we are all excited for this achievement. And just to mention, so in the space science sector, I am here. I work for robotic exploration missions. So that are, when we make observations using telescopes that are on Earth orbit, we do what we call astrophysics and cosmology. Sometimes it's, we link this area with observation of objects that are outside of our solar system, usually. And for astrophysics, the range of frequency that we can observe lasts from the very high frequency of gamma ray to the lower one. When we are able to use a satellite, to use a probe, to use a lander or a rover that can be moved to physically to a destination, usually in our solar system, we do what we call robotic exploration. That is usually in preparation, sometimes, not usually, sorry, but sometimes is in preparation of future human exploration, the one that all we want to do with the best explorers that are humans, of course. But this kind of exploration is limited to the destinations that can be reached and that are not so hostile, that are not so, where the environment is not so harsh, where the humans can live, of course. And currently, our targets are the Moon, Mars, hello, welcome, and future Mars, of course, as you are probably aware of. Hi. So these are what we have the traditional areas for space science. But recently, we had new sectors that are the astrobiology. This is related to the search of traces of organic molecules and then of possible presence of past life. Space weather, that is more related to the environment that is generated by the radiation, the one coming from the sun and the other from out of our solar system. And all this kind of environment is quite harsh. When we are on the Earth, we are partially protected by our electromagnetic field, while when we are outside, we're exposed to a lot of radiations. And I have to say that this is one of the main issue for space, for human exploration for the future. And then recently, we had also the confirmation that a structure similar to our solar system is not so rare. They are very common, and there are many stars that are surrounded by planets. So the study of this, the identification, and then the study of these planets from so far, it's one of the it's one of the most promising branch of space science. This is so the environment. We will focus, hello. We are, of course, talking about asteroid in this specific talk. And you know, this topic that generates a lot of interest, especially because you know, there is kind of scaring and effect that is mixed with curiosity and interest. And this quote is the one that is typically used to, you know, to joke on this topic that is, of course, that has a real base of possible issues, but is currently under control. How it's under control? First of all, we would like to monitor, you know, to have a proper monitoring of what is coming from outside. And sometimes you can find on the news that there is possibility of you know, that we can be scared of possible close pass of asteroid, but this is not the case. When they pass, they are very far currently. All the asteroids that are known are currently well monitored, and they're not an issue. And for this, NASA first is implementing the planetary defense program that takes care, first of all, of the search, detecting, and tracking of all these objects that are there out. And it is mainly based using telescopes on the Earth. Then they must be studied and classified and identified and characterized, of course. But what especially your agencies start doing is to mitigate the risk coming from possible future issues coming from asteroids. And in this sense, DART mission is the first active exercise of deflection. You know, for sure, the objective of the missions that are to deflect, to test the kinetic impactor as a technique for deflection of the trajectory of an asteroid. So I'm sure that you heard that in 2 days, this space probe will be launched toward the asteroid, the moonlet of the binary system that is called Didymos. And this is the first exercise to move from just observation, characterization, identification that currently is giving a good confidence that everything is under control, but for future possible, you know, warning, DART mission is the first attempt to be active in this environment. And in this sense, you will probably are familiar with the mission that will satellite itself will impact on the moonlet of this binary system. The size of this small satellite is about 160 kilometers, so it's about the size of a football field. And the effectiveness, the success of the mission will be measured by telescopes on the Earth. Hello. And in this sense, hello, welcome. So this deflection will be measured after some times by telescopes on the Earth, and the target is the secondary of this system because it will be easier to measure. If you want to measure the deflection of trajectory of a large satellite, of a large asteroid in its orbit around the sun, it will be a little bit difficult. While in this case, the orbit of the small one that is orbiting around its big brother, it will be easier to be measured. So DART, after 11 months, will impact on the secondary asteroid. But 10 days, so again, they intend at the beginning and also now to measure by the telescopes. about 4 years ago, the idea, we shared the idea of adding a witness of this impact. That will be this small satellite that is LICIAcube, that stands for Light Italian Cubesat for Imaging of Asteroid. And it will be the travel companion for 11 months, and then will be released 10 days before the impact, so that can collect pictures of the impact itself, of the effect of the impact. So not only the measurement from the telescopes, but also information coming almost in real time. So DART plus LICIAcube will be the first testing. And after several years, the Hera satellite will be launched. It is in preparation by the European Space Agency. And that mission will characterize the asteroid with much more details than our satellite. So I told you that LICIAcube is a CubeSat. But what is a CubeSat? CubeSat, there is a standard for small satellites whose basic element is a cube of 10 centimeters of dimension, you know. So this is Professor Twiggs that started with this idea. I think it's from California. I don't know which university it was, but it was. Yeah, this is a good idea to benefiting from the miniaturization of the electronics, especially. He also moved with this idea to have small elements that are also modular. So this is the basic, what we call the basic unit, 1U. LICIAcube, for example, is a 6U CubeSat. So it's made by 6 of these small pieces. The size is the sum of these 6 elements. Anyway, this is what I'm mentioning here is the first experience that we made at the Italian Space Agency about 10 years ago of embarking. There were 9 CubeSat on board of this satellite. This was called the LARES. It's been launched in February 2012. And in these deployers, we had 3 deployers, each of them containing 3 of these small CubeSat coming from different European countries. So after the main satellite, they were deployed like this way. And this is one of them, of that 9 CubeSat. So in that occasion, we understood that CubeSat are a good way to involve small countries, to involve not traditional entities in the space sector, because they are faster for the development, they are cheaper, of course. And so we started, I started with this project that at the time I was working for an Italian base that ASI has in Kenya, in Malindi. And so we involved the Kenyan Nairobi University in the development of a CubeSat that has been released from the ISS, International Space Station. And it was the first experience in that case for the Kenyan partner to have an Earth observation system. It is still working, capturing images of the Earth from the orbit. This is another project that we have at the Italian Space Agency. Is based on 6 satellites. Which is the size of this CubeSat? You know, I'm sure. What is the size? This is 1U, right? So they are? Yeah? They are about? It's 3U. This is a 3U CubeSat. That's fine. This is a 1U CubeSat. And we will use 6 of these 3U CubeSats for monitoring gamma ray burst. That is an astrophysics phenomenon of very high interest. In 2014, we were also involved. We applied to a call from NASA to provide the SLS interstage with some, this is a stage of the Space Launch System that can accommodate dispensers for CubeSat. And they are carrying 10 US Cubesat in the launch that is expected in February next year. You are familiar with Artemis 1 mission, for sure. Why not? Okay, NASA is preparing the next generation of missions to the moon. Yes.
Is the nuclear reactor on the moon plan part of the Artemis mission?
This is amongst the possible technologies for power generation on the surface that they expected in the second phase. Yes, Artemis. Yes, yeah. There's two phases. The first early phase is now running, and NASA is preparing these 3 missions: Artemis 1, 2, and 3. The first one will be used to check on the rocket, of course, performances, but also the Orion capsule. The Orion capsule is the next capsule, like the Apollo one, that will carry astronauts again on the moon surface. Okay, so during the first mission, there will be no astronaut on board. It will be just a testing. While in the next one, there are, I think, 2 astronauts that will make this mission not landing on the moon, but having this orbit on the other side. While with the third one, NASA intend to take again humans on the moon surface, a man and a woman this time. Okay, it was planned, the third mission was planned for 2024, but now it's being moved ahead. But anyway, I think in 1-2 years more that they will be able to do it. So in this first mission, there was a room for 13 CubeSats, because what is good in CubeSat is that they are light, they are small, and they can be used for one specific simple mission. They are like this size, you know, that you can handle, you can carry with you. While usually the size of a satellite is bigger. DART is like, I think it's bigger than this size, of course. And but the traditional satellites are really big, really heavy. They can reach 1 ton, even more. When they are like a small car, so you know they're big. They are, and to develop a traditional satellite, it's necessary usually 5, 10 years, 15 years. It's a long time. You can start with the project. It's a long time. They are expensive. CubeSats are not. They are very small, and you can handle a mission in a few years. You can be ready to launch something, and you can test it. Of course, they have not the same level of resources. They have a shorter life. The cameras on board, the instruments are smaller. They are not so performing, of course, but they are good for one specific application. Okay, you can think them like something that can be used for this specific purpose. Again, NASA has room for 13 CubeSats. 10 of them are from US countries, US universities. 2 of them are from Japan, and 1 has been offered to Europe. And the European one selected was this Argo Moon satellite, whose size is not so difficult. This is a 1U, about 1U, right? So there, it's 20 centimeters, 10 centimeters, and 30 centimeters. So it's made by 6 units. Okay, it's 3 like this and 3 like this. So there are 6 units. This is a 6U CubeSat. These are the solar panels that are usually deployed, stowed like this, and after the release will be deployed in order to capture solar radiation and to generate power on board. So during this first NASA mission, we will be released, this satellite will be released and will collect picture of the launcher itself and other picture of the moon and of the Earth. So this was already in place. This project started 2014. In 2017, I was at the Italian embassy in Washington, and I was presenting ASI small satellites for international cooperation. While at the same meeting, there was this guy, Andy Rifkin, that is the DART PI. So we had already had in mind there was this idea to provide the DART with a companion, and I presented ArgoMoon together with this other satellite. And it happened that from that day, the idea of having a satellite that will fly with DART and we collect picture became more real. And so LICIAcube started in like 4 years ago, 4.5 years ago. This is the mission profile. Will be launched in 2 days, maybe 1 day and some hours, and will be released 10 days before DART will impact on the asteroid. Will be released, and we'll have a maneuvering in order to observe the scene of the impact. And then we'll transmit. This is, the scientific phase when DART is coming and LICIAcube is collecting pictures. And then we will transmit the pictures back to the Earth. In order to implement this cooperation, we had a kind of double team structure. This was already in place. NASA was already working on DART. So we were, we started cooperating. The two agencies, of course, they decided how to implement it. Well, NASA let the Johns Hopkins University in Baltimore to be in charge of the DART mission, while the agency, we, NASA in Rome, we involved this Italian firm and these universities and other entities to work on the science that is behind the LICIAcube. And what is the science behind the LICIAcube? The first objective is to testify the DART impact, to be sure that it happened and that they were able to identify the target and to navigate. You know that on DART, there are several new technologies on board of that satellite. And anyway, the mission also for them is quite challenging to identify that asteroid and to precisely impact. Hopefully not on one side, but in the center, because if you want to change the velocity that is their object, is to change the velocity of the asteroid that is orbiting around it. So they want to impact as much as possible close to the center of this asteroid. So the main objective of LICIAcube is to check that the impact happened, and then we have to collect some pictures that have specific purposes. As I mentioned, the measurement of the orbit will be measured by the telescopes, and also then the European mission will reach the asteroid for a very long investigation. We are like the witness that will collect pictures for the most immediate effect. Okay, the most immediate effect is this, what we call the plume. After the impact, we expect that some materials will be ejected and will create this kind of tail, this plume. What we don't know is what is the composition of the asteroid, which is the composition. So depending on the composition, if the asteroid is very bulk or it's rebel pile, it's made of an aggregation of small pieces. This is unknown. So in these cases, the plume of material could be very different. We can expect that if it is very soft, DART will be like, yes.
So this DART mission could have no effect on the orbit of the asteroid, possibly.
Second?
So so this dart, when it hits this asteroid 650803, 68053.
It's 160 meters.
Right.
Size.
So it's a very small asteroid. When it hits, there's a possibility that nothing could happen to the asteroid because the composition is unknown.
Right. We expect that the compactness of the satellite is it's good enough. It is a bulk body, but in the middle of these two extremes, very bulk or very loose, that there are all possibility of composition. And of course, what is doing, they are looking for an impact that is like as much as elastic as possible, like two balls impacting. But if one of the ball is like a snowball, you could have like kind of an impact that is completely different. But anyway, this should be not the case because the asteroid has been studied from telescopes from the Earth. So we expect that the impact will be a kind of elastic impact when dart will, not exactly elastic, but dart will be destroyed on the surface and will transfer energy, will change the momentum of this system. Okay, then it will change enough that it can change its trajectory. LICIAcube will collect pictures of the plume, first of all, and then we'll have the unique possibility to capture images of the other side of the asteroid, because DART will collect also pictures, but only of the face, of the side that he's watching, is approaching. But we don't know anything about this side of the asteroid. We're doing the approach. So in order to reconstruct the shape of the asteroid, we need to have a complete view of the asteroid itself. So after that dart is coming and is impacting, it's destroyed, LICIAcube will be separated and we'll have an observation of the impact itself, of materials, and also of this face of the asteroid. We'll turn the satellite and look at the surface like this. Okay, so then we'll have this volume determination and shape determination. We'll also collect a picture of the surface and look for boulders and for the composition of the satellite itself. Here I put some simple scheme describing how a mission can be generated. How, starting from mission objectives, in the end we will have some real satellite that will accomplish that mission. So we'll have usually change to requirements and then looking for different elements of the system. So the objectives are the ones that I showed before. Collect a certain number of pictures. Okay. Telling the truth, I will remove. That's fine. Okay, thank you. The objectives are usually not quantitative, in the sense that LICIAcube's main objective is to support DART in its mission. Okay, the requirements is something that it's measurable. It's something that I've showed before, that there were numbers like this. Collect at least 3 pictures with this velocity, with this to that kind of particles, and with a specific resolution. Coming from an objective that is very high level statement, you can move to requirements. It is something very measurable. And then from requirements at mission level, you will start thinking about requirements of the spacecraft, which is the orbit configuration, which mass, power, and a lot of elements that can describe into details the satellite itself. In order to fly there, we need a launch vehicle support. This is the one that we obtained from Vandenberg in 2 days. And all the data must be transmitted to the ground segment, to the Earth. Okay, so pictures cannot stay on board of the satellite, otherwise they are useless, and must be transmitted back to the Earth. For the spacecraft design, what is important is to divide all the functions in different subsystems, what we call subsystems. And in short, in simple words, the real core element of the satellite is what we call the payload, that are the instruments. In this case, there are 2 cameras that will collect the pictures. But these cameras must be powered with energy, of course. So we have a power system that is usually based on solar arrays that collect and batteries. Must be maintained at the proper temperature, otherwise if they're too hot or too cold, they will not work properly. They must be protected by a structure. They must be have a software for transmitting back and forth all the elements. And satellite must have an attitude control in order to maintain the pointing. Okay, these are the main subsystems of the satellite. And DART and LICIAcube have them on board. So I mentioned that the core of the satellite is the payload, because the performance, what is really implementing the mission is the instruments that are on board. In this case, there are 2 cameras, and we call them Leia and Luke. They have 2 complementary performances. So one is a very narrow field of view camera with very good resolution on the surface. And the other is has a very wide field of view, but it has a not very appropriate resolution. So one is used to have a, not to look at the details, look at the big picture, while the other is very focused. Of course, the one with a small field of view is difficult to be managed in terms of pointing, because you can lose your target if you're not properly aligned. While with the wide one, you can have a bigger observation of that. Yes, please.
So what would the resolution be of both cameras in terms of something we would know?
Resolution is also linked to the distance. So depending on the distance, I will then describe. But anyway, the best resolution that we can expect is 1 point something per pixel. I mean 1.3 meters per pixel. It means that every pixel can have this. You can appreciate. You can resolve with, I don't know exactly English for, but it's a spatial resolution of the system. Okay, so if you have the crater that we expect will be about few meters anyway. It's not that clear. So we expect to have several pixels describing not so many pixels that can allow us to detect the crater that is being generated by DART. And the real core of the
quick question. So there's only 2 cameras, one for close-up pictures and one for the bigger picture.
Mm-hmm.
What other imaging, if any, were considered? I mean, there's so many different types of imaging, infrared or stuff of that nature.
Yes, telling the truth, the second camera, Luke, has 3 filters that will allow to take what we call RGB, red, green, and blue filters that are related to, that can allow us to make investigation on the composition of the satellite, because they have a spectral capability. From a picture, if you have specific materials that you're observing, they absorb different bands of the light, of the electromagnetic emission, depending on the material that you're observing. So you can have an absorption in a specific band due to a material that is on a surface. So we can identify roughly if it is which kind of minerals are on the surface, okay? And yes, based on the wavelength. Okay, so yes, we will understand something more about the composition. What is challenging in this mission, the most challenging thing, is that, as I will mention later, okay, these are requirements again. You can see numbers again. What is really challenging is that usually when we have a mission approaching a target, like a Mars probe, Mars satellite is going toward Mars, and is trying to be inserted in Mars orbit, it usually changes velocity in order to minimize the relative velocity, so it can be captured by Mars gravity. Okay, it coming and then will approach like this and will be inserted in orbit. But in this case, DART is deliberately very fast against is not changing its velocity. It's trying to impact as fast as possible. And will be released only 10 days before, and we have limited resources on board because the CubeSat is small. So we cannot change the velocity so much. It means that the LICIAcube will pass very fastly towards the asteroid, and will pass very fastly for observing like this, observing the scene. Moreover, we had to define which is the best distance for the observation. Of course, to be closer, it's better because of the resolution. To be closer will allow us to have better pictures. But we have to take care of the materials, of the plume of the materials that will be released. If it will be impacted by a small piece, the mission is lost. So we identified that 50 kilometers is a proper distance, is a good trade-off for be safe during the pass and have a good resolution on the surface. We could be even better, even closer, but 50 kilometers seems to be a good distance. Also the time, the delay when we will pass after the impact is important. We cannot pass at the same time of DART because otherwise the plume will be not developed enough, and the plume needs several tenths of seconds to reach its maximum expansion. So we will pass around the 200 seconds less than, but something like this, so that the plume is properly expanded. And then we have to take care, this is the uncertainties ellipse of our position, because of course in these deep space missions we are at 10 kilometers, about 10 kilometers of distance from the Earth, more than 10 kilometers. It's not too easy to predict and to maintain a specific trajectory and distance, okay? You have uncertainties. Over 10 kilometers, you can have an error of several kilometers at least. So it's very challenging to have a prediction and then an implementation that is very accurate. Moreover, the satellite, as a target, the asteroids are not so well, because they must be illuminated to be visible. Okay, it's not like there are sources that already generate light themselves, but all the other bodies that we are looking for usually are very huge, so they are very clearly visible. In this case, the asteroid is very challenging to be detected. This is an example of an RGB. Sorry. Anyway, during the approach, LICIAcube artificial intelligence on board will use the images of the captured by Leia to identify the asteroid in this black frame. It will be very challenging to do it, because it will be the only moving point in the asteroid. The other are stars, so it must be very smart to identify it. and then to maneuver the satellite in order to have always the camera pointed towards the asteroid. It will be not that easy. We'll be at 6.6 kilometers per second velocity. So it will be very fast. I usually try to say that it's like when you're on a highway, you're driving on your highway and you're very fast, especially when you're close. You want to watch, for example, an accident that was on the road, the side road. If you're on highway and you're very fast, you need to, it's not easy to watch that scene. Anyway, we have to control the attitude and also maneuvering in a proper way. Since there is also a delay at that distance of 10 millions of kilometers, there will be a kind of autonomy on board of the satellite. Okay, so there is not controlled by Earth. At a certain point, it will be autonomously pointing and following trajectories. And this is what will happen. Okay, it's not like this, but DART will open the door and release LICIAcube that is stowed, and then we'll open the solar panels. So, and maneuvering so that while DART is targeting the asteroid and will impact on the surface generating these materials, LICIAcube will be safely following this safe trajectory and collecting pictures that will be transmitted to the Earth. Yes, please.
During the mission, do they ever plan on collecting samples of the Plume?
Say again?
During the mission, do they plan on collecting samples of the Plume?
No. No.
Would that be even relevant?
It would be extremely relevant, but it's quite impossible. It's really not possible. All the samples. Say again?
If you could examine the
it will be amazing. This family of missions that you are mentioning are called sample return missions. They are extremely challenging and difficult. Currently, only the Japanese did sample return from asteroids, and the mission is called Hayabusa. That was completely different idea. They had what they call touch and go. Satellite come close to the asteroid very, very slowly, then touch the surface, collect few grams of materials, and then they flew back to the Earth.
Yes,
it took so many years, very difficult, very...
The previous presentator mentioned something about that. Similar technique. I'm not sure if it was the Japanese.
Yeah, Hayabusa, yeah. They had another concept that is based on a bullet that... Osiris-Rex, yes.
Is that also the same type of collecting of the sample?
Yes, the idea is basically the same. Technique is different, but the purpose is completely different. That is a purely scientific mission. These are planetary defense missions. It's a completely different family, completely different purpose. If we will gain information on the asteroid, it will be interesting, especially because they are binary. It's the first time that we are visiting. It's fine. But the main goal of this family of missions, like DART and LICIAcube supporting, is planetary defense, is to deviate, to deflect the asteroid. That's the purpose. If we will know something, it's an added value. It's something more. It's out of, it's like a secondary objective.
So for detecting the orbit, the change in orbit of the
Dimorphos.
The Greek word for twin. Dimorphos. To measure that, why couldn't they just have another satellite attach itself to the asteroid and detect the satellite or the device that's attached to the asteroid's orbit? And that would
Attach it? What do you mean? Attach it?
Well, have it land, maybe penetrate underground, and then you could determine the orbit from the data you get from the device. Or
yeah, it could be another. Yes, it's another possibility. As I mentioned, The phase approach of DART, it's challenging, but it's driven by the need of being fast, While, and for us, for LICIAcube Satellite, it's already very challenging to approach the target in a way that is not destructive. To have something attached to the surface really need an additional capability of being on board. In particular, the difficulties of these small bodies is that they have a very small gravity. Maybe the only time that for example, in Europe, we try to do something on a small body is the Philae lander on board of the Rosetta mission that visited a comet. The comet is similar in size and somehow composition to the asteroids. Okay, it's a comet. A European probe orbited around the comet for several years, and then released on the surface a small lander with several purposes. For the lander was so challenging to land on the comet because there is no attraction. If you want to land on Mars, it is easy. You can fall on it because it attracted you, as on the Earth, as on the Moon. But it's an asteroid of 160 meters is not attracting you at all. You cannot. You have to stick on it. In fact, Hayabusa lander, Philae, has these 3 legs with the 3 harpoons to try to be attached on the surface. It's not exactly easy. They are very fast. They are very fast objects, and you have no way to capture them. So it's very challenging. So that's why the touch and go, it's challenging too, but it's like you can just pass through. But you want to stay there, it's difficult. Lander Philae had the 3 bumping. At the first attempt, it was like this and went away. It was kind of, and then also Hayabusa had this kind of not exactly precise attaching. They are very small. The gravity is so small. Anyway, no, it's an interesting question, but in the end, the measurement from the Earth with telescopes is not that accurate, of course, but it's so much easier. While another concept will be extremely challenged and almost not feasible. So a few reference to the phases of the LICIAcube flyby. This is the duration of the phases, very few seconds, tens or hundreds of seconds. And in these phases, we will observe different aspects. This phase is focused on impact, then on the ejecta, and then of the crater, maybe, and on the far side, on the not visible side. What is the hardware that allowed this, that has been generated? These are the main subsystems of LICIAcube and how they were tested. What is very interesting in satellite is that they cannot be repaired, okay? All the even very, very complicated machines that we have on the Earth can be repaired. If you have an issue, you can go there. Satellites, they are not like this. They are one shot, So we need, for very high reliability, we need a lot of peculiar features of satellite. And we achieve this good reliability by redundancy, for example. Some of the units are doubled, of the components are double. So if one fails, you can move to the other. But you cannot not double everything because it will result in a very huge satellite and we want to miniaturize. So we have to double, and here's the smartness of the engineers to identify the precise element that if you can double, you can even go very good in accuracy, and to remove the redundancy of the others that is not needed. Okay, that's very interesting for engineers. And then you have to think about many tests on the Earth that can simulate this. You can see the entrance of what we call thermal vacuum chamber, the chamber where you can create the vacuum as in space. You can now reduce the temperature, so you can simulate the very low temperature in space, and you can make testing to be sure that the electronic is performing good. This is onboard computer, solar array. TT&C is telecom and tracking. It's a communication system. And that one is propulsion system, PS, propulsion subsystem. These are the two payloads with a lot of cables, of course, and Lay and Luke. External battery charger, because must be charged, and this is the dispenser that is hosting LICIAcube. They are currently on DART here, very close. Just to give you an idea, these are the testing that has been performed in springtime in Italy. This is a very small amount of the huge number of testing that has been performed. These are the ones that we call at system level. When you develop a satellite, you need a lot of testing, and you can do them on the final product, I mean on the satellite, or you can do them on its component first to be sure that the components are good. It's like you have a car. If you test standalone all the pieces of the car, when you put them together, you can be sure that it can work. But testing at the lower level, at the subsystem level and standalone system, is very costly. It's long. It's so long. So we accept some risk to do it. Something can be done just in the end when the system is completed. And this is the LICIAcube in a thermal vacuum chamber. This is with the optics that are covered, so there cannot be. This is in a release testing. What is very challenging is usually I cannot see here. Why not? There is no mechanical testing. This is in the other. These are thermal cycles. Up and down temperature to be sure that during this up and down it will survive. While in this case, these are mechanical testing, vibrations, because the most stressful phase for the satellite is the launch itself. When it's on board of the rocket, it's on top of the rocket like this, and the rocket is starting the launching phase. It's vibrating so strong. And you can imagine such a small, and especially for the optics of the cameras, optical spectrometer is a very loading, during this vibration phase. There is also an important source of stress that is the shock, what we call the shock. When there's an explosion separation that is very strong due to separation of the stages, or separation of something that is closer to the instrument, is very challenging. So all this testing has been performed to stress and to check on the withstanding of the satellite. In order to collect the data from LICIAcube, we implemented this side of the ground segment, the part that is on the Earth. So LICIAcube will transmit to the NASA JPL antennas of this space network, Deep Space Network. Here in Goldstone, in Madrid, and in Australia. So all the part of the Earth can be in visibility. And okay, I will not describe everything, but anyway, the data come from Deep Space Network of NASA to Italy. We will distribute to the Science Operations Center the images that will be transmitted back to APL, that is the implementing team for DART mission. So we will share our images with the DART. Anyway, there you can find lots of elements for. This is how finally will be implemented. That one is what we call architecture. At the beginning, we imagine the system like this, and then finally it's more similar like this one. We have a cloud for sharing the data, and this other kind of transmission. In parallel, the scientific team of DART has been integrated with Italians that are now part of the scientific, because they will jointly analyze the data and the images too. And they are already working for prediction of the crater formation, for the prediction of the plume. They're already in touch. They're working together. There were many scientific papers describing. And these are the part of the Italians that are involved. This is Italian. John Roberto Brucato, anyway, seems to be an American guy, but he's from Sicily. It was a surprise also for me. And it's called like this because his parents were Kennedy's fan, supporters. So it's like John Kennedy and Robert Kennedy. So it's called like, but he's a completely Italian guy. And we already made a lot of papers, publication. These are presentation in conferences, already in the prediction phase. We had also some publication on not scientific paper, but on Mickey Mouse and some, because in Italy there is a quite huge interest in this mission, because it's the first Italian mission in deep space. We already provided subsystems, what I call subsystem, part of satellite of international missions. But for the first time, now we will have a completely Italian satellite in deep space. So there is a huge interest in Italy for this. Okay, this is the team. This is the card for Christmas that we sent, and this is these are the guys. They are very young. I can tell you, I'm one of the eldest. They are around 30, 32. It's a very young team, and it's very interesting. I think for them, this mission is a well-training experience. So for the future, we'll have a kind of new generation of engineers and scientists ready for similar challenges and missions. So that's one of my last question. And if you have some further question or interest, we can even talk. Thank you. Thank you.
Yeah, I have a question. I have two questions. So
Please.
The first one I have is, what if DART misses? Will LICIA have a chance to correct itself and still observe the comet, or will it just be like, go in the same route as the DART?
So if the DART will not impact on the asteroid, the primary mission for LICIA, of course, is strongly affected. We calculated possible what we call re-encountering, but also if DART will be good, at the beginning we were hoping that there will be another target, because LICIA is designed to survive in deep space for at least 6 months. So we can, but the problem is that the tank for the propellant for LICIAcube are quite small, because the satellite is like this. It's big like a shoes box, So after that maneuver, there will be not so much propellant to make a big maneuver and to look at another asteroid, unfortunately. So we'll just going on with the technological testing on deep space. We'll try to check if our subsystem will survive. We are going to operating.
And you talked about the different testing for the satellite, such as like vibrations and such. But then another thing that you have to test was the expulsion of LICIA from the DART satellite. Is that another test you had to do? Like another is that another important impact, like you were talking about with rocket separation, that causes a lot of about a lot of shock. So I was thinking, does that a similar shock occur when separating from dark?
Sure. That's an interesting point. You capture, yes, we had a lot of discussion on this topic because the shock derived from separation after dart release is a quite important source of load on LICIA, and we tested it. That's a good point. Mm-hmm. But another good point is that after the separation, dart will receive a kind of force of torque because it will release a mass in one direction. So satellite is something that is, if you give a push in one direction, you will have a change in. So they were scared. You can imagine that the DART team already had in mind their own mission, and then we jumped on board somehow. And they said, okay, oh my God, what can we do? At the beginning, we have to prevent that LICIAcube release will not destroy the solar panels that are very close. So if we can be released in a direction that is not so precise. And the DART solar panels are different. Usually solar panels are hard mounted on surface that is very, robust. DART solar panels are different. For the first time, they will use solar panels that are folded, that are rolled, and will be like the things that are on the window. I don't know how there's English for, but they are rolled. They are rolled and then they are extended like a rolling thing. Mm-hmm. So they are not. Solar panels are not so rigid. So they were scared that after the release, there will be a vibration in the system that will generate a wave, and LICIAcube will scratch on the surface. So we release in a safe direction. Anyway, we worked on many, how to mitigate the presence of LICIAcube on an already existing mission that it was DART. We of course want to be safe for the basic mission of DART. And we had a back and forth on what we called interfaces. And one of the topics was the release, the shock at the release, who is generating a shock on what. Also the door opening, I have to stop on something that is absorbing that vibration. What? You're not convinced, I know.
It has some type of mass, right? Light has mass.
Right. It's called sun pressure.
Sun pressure.
It's one of the disturbances that affect trajectories that otherwise are.
Is there a calculator that calculates all this?
Yes. Depending on the surface, depending on how the surface is large, and it's. But yes, sure. It's one of the effects. These guys that I will introduce you these guys. Usually on Monday we have teleconferences where Andrea and Igor discuss on the elements. Oh my God, it's so cold. Discuss on the elements that affect the trajectories. And one of the elements in their list is solar pressure. And solar pressure is, they debate, did you consider solar pressure? Yes, how much? And it's one of the elements, the component for. And if they include or not include the trajectory change of several tens of meters. In this case, because LICIAcube is quite compact and has small wings, but if you have very huge wings like DART, solar pressure is not so negligible. I'm sure that they need to model it.
What else do they have to take into account?
There are gravitational effects, and there are several effects. The others are usually related to gravity. In this case, there are not so many. But if you have satellite orbiting around the Earth, you have to consider the fact that the Earth is not a perfect sphere, the fact that the mass of the Earth is not perfectly distributed. There is a set of the electromagnetic field, how the electromagnetic field is. All these are elements of disturbances on a satellite orbit. In this case, we have not them. It's easier, a little bit easier.
So the technology that's on the LICIacube, is it similar technology to what's inside the DART in terms of like, for example, propulsion system, or in terms of the solar panels, or is it just completely two different technologies?
Propulsion is quite completely different. While solar panels, LICIacube is based on more traditional technologies for this specific functions, because we want to minimize. Okay, in space technology, you have to innovate when it's needed. Okay, if you don't need to change something, it's not that you have just to. Okay, it's an innovative field, of course, when you need different performance. Okay, but if you have a consolidated technology like power generation, batteries, onboard computer, something that is already working, has been proven that works in space, usually we prefer to use that one, because we have focused the innovation in something that is, that is specific for that mission. All the elements that can be general purpose, that it's good for a wide range of satellite and application, they are good. If DART has a completely different kind of propulsion. We are more traditional. We call the gas expulsion. They are testing a new technology based on electric propulsion. They are using a different solar array system, while our wings are good. And then we have, I think I can say that LICIacube added value is of course on the intelligence on board, on the software that will analyze all the information. But yes.
So we're trying to kind of like identify the type of material the asteroid is composed of. And I was wondering, have you guys what's this bridge called? Like kind of guess what the material is? Like, do you guys make guesses already? And if so, what are some of the guesses you guys have made of what it's composed of?
This is not exactly my field. I am, as an engineer, I'm in charge of the whole mission. Then there is a group of scientists I can introduce you to them that they are focused on the guessing of the materials composition. They are doing it by observation from the Earth, and I know they are quite confident, at least on the family of the asteroid. So they expect no surprise on the composition. And this will be confirmed, of course, after our mission. But the final, characterization will happen with the Hera mission, the European one. They will have like 3 years. We'll stay there like 300 seconds. They will stay there 3 years, observing with at least 6 instruments and 2 Cubesat. Hera will also have 2 Cubesat as companion for observation. So we have complementary objective. LICIA is the witness, immediate witness, while this there, and of course we have different costs. LICIA is costing, I think, much less than. Okay, Cubesats are focused on a specific function. Okay, and they are cheap, quiet, and they are small, and they are easier. So you have to think about them as a complementary element in a mission. For what concerns the composition, we will have lots of confirmation on the hypotheses that are currently on the table.
What do you think the composition is now based off the data?
It's quite bulky with some boulders. They expect some boulders, but a quite structured and compact element.
And are there any proposals for LICIA 2 yet? Or are they thinking about it, LICIA 2 or 3?
I mentioned that LICIA somehow derives from Argo Moon, that other mission on Artemis 1. So what's good in space, that when you have a good concept that you can customize, you have a platform that can work in several similar missions and for similar application. So we expect that some other future deep space mission that will need an imaging system can be supported by LICIAcube 2, for sure. And I think if you have a good idea on that.
I will be looking for LICIA 2 and LICIA 3.
Me too. I will have. It's.
So we're running over a little bit, but I want to thank all of you. And
Thank you.
Simone. This is just a little token.
Oh, thank
From
you.
Hancock. Their wine is pretty good.
Ooh.
Yeah, and that's,
Ooh.
thank you for taking time out of your
Thank you. Oh my, it's yours. Wow.
yeah.
California's known for its wine. Or at least the Central Coast.
I